All right, we'll get started this week. I'm happy to welcome and introduce our DLS speaker this week, Dr. Tara Shreve. Tara is an InSAR specialist called Geological Survey, Geologic Hazards Program, August. Prior to joining the survey, Tara was a postdoc fellow at the University of Alaska Fairbanks. Prior to that, at the Earth and Climate Lab in Washington. Tara earned her PhD and master's from the Institut de Physique de Paris in France, obvious, where she studied crustal deformation related to igneous processes in InSAR. And she has a bachelor's of science in math and a minor from the American. Tara continues to study volcanic processes with InSAR. We're going to hear about some of that today, but has expanded her expertise to ground deformation hazards more immediately relevant to about that today, I think, including things like landslides, groundwater, basin subsidence, and more. She also has some really great science outreach activities. Crash Kino. For you to ask her about this. Cool. I have some videos on my phone. Very popular with middle school kids. Very fun science outreach. So ask her about it. Thank you for sharing your work and joining us today, Kara.
Yeah, and thanks, Pete. Thanks so much for inviting me. It's a pleasure to be here to talk about some of my PhD work and some work that I'm doing currently with the Utah Geological Survey. As Pete mentioned, I work in the Geologic Hazards Program, and I'm working as an interferometric synthetic aperture radar, or InSAR specialist, to look at displacement across the state of Utah related to geologic hazards. In this talk, I'm going to be focusing on two different research topics. And before I start, I'd like to thank all of the collaborators who helped with this research during my PhD and postdocs, as well as my colleagues at the UGS who helped me get my feet under me as I'm learning about the geology and geohydrology of Utah. So I'm going to start with some background on the technique of InSAR, go into two different applications of InSAR Geodesy, the first being related to an eruption that happened in 2018 at the volcano Ambrim, which is located in the Southwest Pacific, and then talking about land subsidence that is ongoing in the state of Utah related to groundwater pumping. I'll take a little pause in between these sections if we have enough time to take a few questions, since these topics are pretty different. The two science questions that are motivating and guiding this talk are first related to volcanic eruptions. What are the precursors that are observed at open vent volcanoes prior to eruption? And the second being how much aquifer storage loss is occurring in Utah due to aquifer deformation from groundwater pumping. Before diving into the results, I know we have a variety of backgrounds here, so I'd like to talk a little bit about the technique of InSAR and how we can use it to measure ground displacement. InSAR uses synthetic aperture radar, or SAR, acquisitions, which are fine resolution images from a radar system, which can be mounted on any moving vehicle. So this can be a car, a plane, but in this case, we're looking at SAR sensors that are mounted on satellites. So we have systematic acquisitions across the entire globe, allowing us to have consistency in our measurements over time. Interferometric synthetic aperture radar, or InSAR, is a technique that uses two of these SAR acquisitions in order to measure the amount of ground displacement towards or away from the satellite at a particular spot on the ground. We can see here a simplified example of how this technique works. Because we have, this radar signal has an amplitude and a phase. If we have a change in the phase between 2 days, then we can use this to relate to the amount the Earth has moved in the direction of the satellite. In this case, we have a volcano that on day 1, nothing very exciting is happening, but then on day 2, we had an eruption. Magma evacuated from the storage region underneath the volcano and subsidence. Between these 2 days, because the ground moved, we have that phase shift or phase change, the red portion of the phase, and we can find this phase difference in every pixel or resolution cell in the interferogram, and this creates a displacement map of the region of interest. One of the strengths of SAR is that it's an active remote sensing methodology, which means that it provides its own illumination and it allows us to be able to image day or night and regardless of cloud cover. This is in contrast to something like optical remote sensing, where if we have clouds, we just can't see the Earth's surface at all. So it's quite useful in response to natural hazards when we need to see the Earth's surface with rapid response. We've all probably seen optical satellite images or false colored images. Radar images are slightly different. We can see here the amplitude and phase from a SAR image of the Salt Lake City International Airport from a Spanish satellite called PAZ. What we see in the amplitude image is some pixels that are very bright, and this is related to areas that have a high amount of energy that's backscattered to the satellite, and then areas that are darker where there is less backscattered energy, and these surfaces are considered smoother on the wavelength of the satellite's signal. The phase for a single image looks random, but when we take that phase between two different days, we can create an interferogram. And so this is where we can measure that displacement between those two time periods. This is an example from Ambrim volcano. We can see all of those color cycles, which we call fringes in InSAR speak. And if we assume that there's a point in this map where we have no deformation, which could be on the western flank of the volcanic island, if we count the number of phase cycles, we can relate this to the amount of displacement. So here we have about 12 phase cycles, and the wavelength of the SAR sensor is 24 centimeters. And each phase cycle is going to be 12 centimeters. So here we have over a meter of displacement associated with the dike intrusion. This displacement is a 1D displacement away from or towards the satellite. And that means that it combines, has a component of both vertical and horizontal motion. So with a single image, we can't normally decompose those two components. And so here that motion towards the satellite is both vertical motion, but there may be some eastward motion as well because the satellite is looking to the west. That direction that the satellite is looking is called the line of sight, or LOS. And so in some of the images or maps that I'll be showing, there will be little arrows, and those arrows are going to tell you about the direction the satellite's looking. In the past 30 years, the number of civilian SAR satellites that are in orbit has increased dramatically, as we can see in this chart. The first SAR or InSAR applications were available in the 1990s. And today we have over 10 different civilian constellations that can be used for science applications. Choosing the right mission or constellation for what you're looking to do depends on a few things. One of them is the wavelength of the SAR sensor. And for InSAR applications, this is normally divided into 3 different bands: X-band, C-band, and L-band, with L-band being the most useful for penetrating through vegetation. Although as you have shorter wavelengths, like with X-band, you become more sensitive to smaller amounts of displacement. In addition to an increase in the number of satellites that are in orbit, we also have an increase in the number of services that are available for people to use InSAR. One example is the Jet Propulsion Laboratories Opera Displacement 1 product, where they're working to automatically process all of the European Space Agency's Sentinel-1 satellite data over North America. This is an example of some of the automated processing that they have done so far and released. And so basically you can go onto their website and you can just interactively look at different areas of the United States and see if there's any displacement that can be measured with InSAR in that area. Of course, these are automated products, so there are things to keep in mind and noise that can't be fully corrected, but it's a great place to start if you're interested in working with InSAR data, but don't necessarily want to do all the processing on your own end. In addition, recently we had the very exciting launch of the NASA ISRO SAR satellite, or NISAR. This was a joint mission that was funded by NASA and the Indian Space Agency that launched in July of 2025. This is the first L-band SAR sensor on board a satellite that will systematically acquire around the globe twice every 12 days. Again, these longer wavelengths are really useful because they penetrate through vegetation. I'll show some interferograms that are over a tropical volcanic island. And so even dense jungle can be penetrated by these longer radar wavelengths, which is very useful for applications such as monitoring volcanoes, earthquakes, and other large amounts of displacement. The initial products from InSAR were launched in were available in February 2026, and more calibrated operational products will be available coming this summer. So we're all really excited to be working with this pretty large and really novel data set. Here's an example of a displacement map that was created using InSAR from an eruption that happened in Ethiopia. This volcano erupted for the first time in 12,000 years. And so this is really the first time displacement has ever been measured at this particular volcano related to an eruption. So here we can see those lobes of displacement related to a dike intrusion or magma intruding into the crust. All right, so jumping into the first InSAR Geodesy application, I want to talk about some work from my PhD focused on Ambrym volcano. And the question again we want to answer is regarding precursors at open vent volcanoes. From a classic geodetic perspective at a closed system volcano, there are a few different ways to think, or there are a few different ways that scientists or there are a few different ways that volcanoes can behave before eruptions. And here's just an example of some of the types of deformation that can be measured prior to eruptions at these closed system volcanoes. This is due to an influx of magma into the storage region, causing pressurization and uplift prior to an eruption. The final threshold of when there's actually a rupture of the chamber wall and propagation of magma towards the surface is still something that's an active area of research, but there are some volcanoes where this uplift is systematic enough to be able to use it to better understand when the onset of an eruption will happen. However, at open vent systems, these precursors can be more enigmatic because of the connection or the consistent connection between the magma storage region and the surface. So not all the open vent volcanoes are created equally. Here we can see an example of the continuum of different types of open vent systems, with their similarities being that there's some type of consistent connection between where magma is being stored and the surface. On the more open side, we have the example of Stromboli, which has been more or less continuously erupting for 1,000 years. And then on the less open side, we have Mayon in the Philippines, which has persistent summit degassing, indicating that there is some connection between the outgassing of magma at depth and the surface, but we only have moderate-sized eruptions every decade or so. Here we can see a compilation of the open vent systems around the world. We can see that they occur in many different tectonic contexts, as well as with different compositions of magma. What we're going to focus on in this presentation is the volcano Ambrym, located in this corner of the world in the Southwest Pacific. And Ambrym, between 2005 and 2015, was the highest passive volcanic emitter of sulfur dioxide in the world. If we zoom in further to the region of interest, we can see the central portion of the New Hybrids Arc and subduction zone here. This is where some of the most active volcanoes in this region are located. Ambrym is shown in red, and Ambai, or Aoba, is also shown in just above it. In the central of the New Hybrid subduction zone, we have the collision and subduction of the D'Entrecasteaux Ridge, which reduces the convergence rate from 9 centimeters per year in the south to 3.5 centimeters per year in the central segment. This results in compression in the central segment of the subduction zone and growth along the back arc thrust belt, which is shown in blue. If we zoom in even further, here we have an optical image of Ambrym where we can see the persistent plume that's due to the persistence of active lava lakes within its main caldera. Here we can see some examples of these lava lakes. There's only a handful of volcanoes in the world that have active lava lakes, and Ambrym has been hosting at least 3 since the 80s and probably earlier until 2018. We can also see some photos from our collaborators who made it into the field, who were looking at degassing and doing some gas geochemistry and flux measurements from the lava lakes themselves. So these lava lakes are located within Ambrym's 12 kilometer wide caldera. This is one of the largest basaltic calderas in the world, on shore or on land. And the mechanism of formation of this caldera is still debated, whether or not there was a Plinian eruption that resulted in caldera formation about 2,000 years ago, or whether there is lateral magma migration, which causes a more episodic subsidence of this caldera over time. Within the caldera, there are intrusions and eruptions that occur, and here are just some examples of those lava flows that have been mapped since the 80s. In addition, there are 2 rift zones that radiate bilaterally from the central caldera, and there have been lava flows that have been mapped along these 2 rift zones in both the 1800s and 1913. This most recent eruption in 1913 caused a phreatomagmatic eruption on the western coast of Ambrim, which destroyed a hospital. So you may have noticed that Ambrim is located in a remote region of the world, and so it can be difficult and expensive to maintain instrumentation here. And so one way that we augment our knowledge of this volcano is using satellite-based remote sensing data. And in this presentation, I'll talk about InSAR, but also incorporate it with some other remote sensing observations to try and better interpret the data that we have. We're going to be looking first at passive degassing that was measured using the ozone monitoring instrument aboard the AURA satellite, which was launched by NASA in 2004. And then also looking at ground displacement from the European Space Agency's Sentinel-1 SAR satellite, which was launched in 2014. Here we can see first a time series of the daily sulfur dioxide mass that was emitted from Ambrim. There are volcanoes nearby, and so once we remove the contributions from those degassing volcanoes, we obtain the dots that are in red, which we can convert to a SO2 flux, which is about 7,000 tons per day of sulfur dioxide emitted from Ambrim. Here we're focusing on the time period of 2014 to 2018, as this is after the launch of the Sentinel-1 satellite. And we can see that in 2018, that SO2 flux decreased dramatically and then ended completely after the 2018 eruption. We can also see in the bottom of this slide some optical images showing that in 2016, there were at least 4 active lava lakes at Ambrim. And in November of 2018, about a month before the eruption, that number increased as we had possibly increased heat flow to the surface prior to the eruption. In addition to passive degassing, we can also measure subsidence that happened within Ambrim's caldera prior to the eruption. Here we can see an InSAR velocity map that shows that there was up to 10 centimeters per year of displacement within Ambrim's caldera. And here is a time series of a point in the middle of that displacement map. The orange dots on this plot are the thermal anomalies related to the lava lakes, and we can see there's not a huge variation in that over time, as we also saw with the sulfur dioxide degassing. What we can see is that in the ground displacement, there's that consistent subsidence, and then we have a kind of evening out of that trend and a cessation to that subsidence in October of 2017. This subsidence ends pretty abruptly about 2 months after an increase in seismicity at Ambrim, and that eruption began in December of 2018, about 14 months after the end of that subsidence. So on December 14th of 2018, an eruption began at Ambrim within its central caldera. We can see here the lava flows that were emitted, and the stars relate to the fissures that opened and caused lava fountaining in this central region. We had a fortuitous acquisition from a SAR satellite on the 15th of December, and so we were able to measure the displacement that occurred related to this, just the fissure eruption within the caldera, which is what we see here. The red area is the area that experienced motion towards the satellite related to a dike intrusion that fed that fissure eruption. We then were able to, there was another acquisition later in December that measured ground displacement at Ambrim, covering the entire eruptive episode. And here we can see a much different picture. Instead of having that localized deformation just near the fissure site, we can see that basically the entire caldera is subsiding and that we also have uplift along the southeastern part of that rift zone. So this indicates that there was a migration of magma tens of kilometers away from the central caldera, which possibly erupted offshore. Other indications of this migration of magma is that we had a migration of seismicity away from the central caldera region, starting on the 15th of December after that initial fissure eruption within the caldera. During this time period, there were also multiple long period events that were recorded that had focal mechanisms that are possibly related to reservoir volume loss or caldera ring faulting, which relates to that large subsidence signal that we saw around the caldera relating to the evacuation of magma from the storage region. We did have collaborators in the field who were able to confirm that there was a basaltic pumice that was found offshore, and so there was a submarine eruption, although there was no lava that erupted along the southeastern coast. There was also reef uplift, which confirms the uplift that we measured with InSAR, and then there was faulting of more than a meter in some of the villages along the coast. So this was a pretty significant amount of magma that caused displacement along Ambrim's eastern rift zone. So with the deformation map from InSAR, we're able to do an inversion to estimate the amount of magma that intruded into the rift zone, producing this displacement at the surface. Here we can see the model that explained the deformation. We had a plane that's propagating along that eastern rift zone, and then we find the amount of opening along many different small subsections of that plane, and we invert for the best opening that explains that deformation at the surface. We find that within the rift zone, there was about 475 million cubic meters of volume change within the rift zone. And we also modeled the depth and volume change of a deflating point source beneath the caldera. And we estimated about a 213 million cubic meter volume change of that deflating source. We also found that the maximum amount of opening at the surface was offshore, and this is consistent with the fact that there was a submarine eruption. So to go back to our question, what were the precursors for this 2018 eruption? Some clues that we have compiled is that before the eruption, there were persistent rates of passive degassing with very little change before the eruption. There was also subsidence and a change in the subsidence rate, basically ending of the subsidence 14 months before the eruption. And we also saw new vent formation, indicating an increased heat flow to the surface. With these clues in mind, we want to try and think if there was magma replenishment of the shallow chamber, but this maybe didn't manifest as uplift at the surface. One model that had been described in the past to explain subsidence at volcanoes is that of mass loss from a magma storage region due to outgassing of magma and degassing to the surface. We chose to apply this model at Ambrim because of the persistent high rates of degassing that were measured. This model, conceptual model, is shown here. I won't go into too many details, but you're free to look at the papers and read more about that. But basically, the idea is that you have a reservoir volume decrease or depressurization from that mass loss from the gas that's leaving the system. And you can also have a reservoir volume increase or repressurization from magma replenishment. If these two balance out, you can have no net reservoir volume change. So using this lumped parameter model, we tried to explain the geodetic time series that we had by constraining the parameters from the degassing observations and also the geodetic models and the depth of the magma storage region. We found that with a wide range of reservoir volumes and conduit radii, we're able to explain the depressurization rate within the chamber from the rate of degassing at Ambrim from 2015 to 2017. And we were able to estimate the amount of volume intruded needed to balance that volume loss due to degassing. What we found is that about 0.16 cubic kilometers was necessary to balance the volume loss from degassing. And if we remember, the volume change within that storage region that we calculated from the geodetic modeling was about 0.21 cubic kilometers. And so we have a fairly decent agreement between those two volumes of the amount that possibly intruded into the reservoir region but did not result in uplift, and the amount that was evacuated from that chamber during the eruption and rift zone intrusion. So the conclusion from these studies was that magma replenishment may have began in October of 2017, 2 months after an increase in seismicity, but it did not significantly pressurize the reservoir and result in uplift at the surface. One of the other observations that was really interesting at Ambrim is that after this eruption, basically the lava lakes drained. There was collapse of these craters that hosted the lava lakes, and we had no more degassing. So that 7,000 tons of sulfur dioxide just completely stopped. And what we saw in the months following the eruption was we saw some continued subsidence for about 9 months, and then we saw a very fast uplift. And this is the first uplift signal that had been measured at Ambrim in 2 decades, or more than 2 decades. So basically when we had geodetic measurements from satellite. So here we can see, again, this is Sentinel-1 data with acquisitions every 12 or 6 days. And we can see that between 2019 and 2022, we had anywhere between 30 centimeters to 80 centimeters of displacement or uplift at Ambrim after the system essentially became closed and that degassing ended. Here we can also see optical images comparing November of 2018 before the eruption and August of 2020 after we had the closure of that connection between the storage region and the surface. To go back and answer or to contribute to our science question we had at the beginning of the presentation, in terms of precursors at open vent volcanoes, Ambrim is one example where we demonstrated the importance of the eruption precursor is the change in the time series. And this really emphasizes the necessity of having a long time series in order to establish the background for a volcano, which many observatories have been working towards establishing these backgrounds for many decades. And so, especially at open vent volcanoes where we don't see this uplift prior to eruptions, understanding the background state and any variations from this can be indicative of possible intrusion or change of the magmatic system. Some outstanding questions from this study is that we don't have any observations related to recharge in the days or hours prior to the eruption because we didn't have anyone in the area at the time, and there was only one seismic station on the island at the time, which didn't record any measurable seismicity directly before the eruption. And this, the days and hours before is still a time frame that is not accessible with satellite imagery. And then we still also don't know what the final trigger that initiated the eruption was, and we still don't understand why we had that migration of magma tens of kilometers into the rift zone when we initially just had that localized fissure eruption. All right, so I'm gonna take a second here and let everyone digest and ask some questions because the second half of the presentation is gonna be on a pretty different topic. So I'm happy to take a few questions or we can just move along. People don't have any. Like a explosive, like Plinian style eruption. I think it depends on the amount of recharge beforehand and how the crust is responding. That's a hard question to answer. Sometimes at volcanoes where we have really explosive eruptions, they haven't erupted in 10,000 years or in a really long time. And so we might not have that background monitoring of it. So it becomes even harder to be able to forecast when that might happen. The one advantage of satellite data in general is that you do have acquisitions across the entire globe. And so there are people who are working to have systematic deformation monitoring at every volcano that's basically erupted in the Holocene. And so even if a volcano isn't monitored by an observatory, you still may see changes in those satellite observations that create an alert within their systems. So satellite data is useful, but the science is, complicated.
Is the resolution?
Yeah, and so there's two types of resolution. There's the spatial resolution of a pixel cell. For this Sentinel-1, the systematically acquiring satellite, it's about 15 meters in terms of spatial resolution. And then there's the actual sensitivity to displacement. The smaller wavelengths can measure, so you can also produce a time series with InSAR, and so you can get rid of some noise using redundant measurements. And if you have deformation happening over a long period of time, you can measure 5 millimeters of motion per year. So pretty small measurements. In a single interferogram, you're constrained depending on the wavelength, and it can be anywhere from 5-8 millimeters to a centimeter.
So that particular levels out, has that been seen other?
Yeah, that's one thing that's interesting is this model that had been developed to explain subsidence at volcanoes had never really been applied before. There hadn't been a volcano that was passively degassing with geodetic measurements where they were seeing this subsidence. I mean, you do see at restless calderas, like silicic systems, you see periods of deflation and inflation, sometimes relating to crystallization that's happening in the reservoir. But this subsidence from degassing, Ambrim was, as far as we knew, one of the first examples of it. Yeah, so generalizability, every volcano is very different, but it is something to keep in mind when you have these passively degassing volcanoes, which that is at open vent volcanoes, that is common. Yeah, that's a good question. InSAR has two bands. It has S-band and L-band. But the S-band, I don't believe, can be used for interferometry. It's used for other applications, more in looking at vegetation and soil moisture. I don't know of any other satellites that have multiple bands because you have to have two separate sensors on the satellite. So it is a more complex system. But InSAR is an example of it is possible.
So like problems with our for a while ago. Heard anything? Problems of getting around?
Yeah, so L-band, so there was a volcano in Alaska. My previous postdoc was in Fairbanks in Alaska. When I was there, there was a volcano called Eniakchak that started inflating. The first InSAR acquisition was in the winter, and it was snow. The caldera was snow covered. When you have dry snow, you can have penetration through the snowpack with the longer wavelengths. But in most cases, generally, when you have snow cover, you just have decorrelation, especially if there's any melt in the snow. I haven't heard of anyone putting corner reflectors on snow-covered volcanoes. They're quite large, and getting them out there, I don't know if it's a priority. I know that they're in locations that are snow-covered in Alaska, but not necessarily on volcanoes. but they get GNSS stations out there and seismometers out there. So if it's a priority, they could probably make it happen. All right, I think I'll hop into the next section and then happy to chat more afterwards as well. So this next part of the talk is going to be related to something closer to home. So I'm looking at land subsidence in Utah related to groundwater pumping and excess of recharge. I just want to point out that these results are preliminary. We're hoping to publish them later this year, but they haven't yet been peer reviewed. So throughout arid regions of the world, land subsidence is occurring in aquifer systems when they become stressed due to groundwater pumping. The stresses within an aquifer are shown in this cartoon, where you have the total stress related to the overburden and the water within the pore space, which is balanced by the pore fluid stress and the effective stress, which is the amount of that total stress that's borne on the rock matrix and sediments. When you have groundwater pumping or withdrawal of water from the aquifer system, you have a decrease in that pore fluid stress and an increase in the total effective stress, because the total stress stays mostly the same. And so you're going to have a compression of those sediments. And if you reach a certain stress threshold, you can have permanent compaction that occurs, which reduces the amount of aquifer storage capacity over time. This is something that has been observed throughout the western part of the US and also other areas of the world. In particular, in the US, California and Arizona, as well as Nevada, have had issues with hazards related to land subsidence, especially earth fissuring, where you can have these tension cracks that form underground. And when you have infiltration of surface water, this causes these cracks to erode. And you can have these large earth fissures that open up at areas of that have a large amount of differential compaction. Here's both of these examples are from Arizona, and you can see a drone flight over one of these fissures. There are some people in the corner for scale, and so they can be quite large and hazardous when they're opening up near infrastructure. Utah's first experience with earth fissures was in the early 2000s, and then in the 2010s, where there was a development by Cedar City in Enoch that had to be abandoned because an earth fissure opened due to subsidence. So this subsidence in Utah has been measured in southwestern Utah, as well as in the northern part of Salt Lake Valley over the past 20 years. Some of the first interferograms that were processed in Utah that measured subsidence were in the 1990s, but there hasn't yet been a statewide survey trying to identify regions of land subsidence. And so the UGS decided that they got some money from FEMA and the Division of Emergency Management in Utah in order to map out these areas so they can be monitored moving forward. In order to do this, we're looking at data from the past decade from Sentinel-1 again. So this has systematic acquisitions every 12 days. And we're using products from the Alaska Satellite Facility Service called HYPE. So they process the interferograms on their cloud servers, and the end users are able to have those interferograms to perform post-processing and create time series of displacement. So you have measurements of displacement every 12 days. Using this survey, we identified 5 new regions of land subsidence and updated measurements at 7 known subsiding locations throughout Utah. Here we can see the general areas where we're seeing subsidence throughout the state. I will have the caveat, because InSAR does decorrelate in vegetated areas at the wavelengths we're working in. There could be areas that are subsiding that we may not have measurements from InSAR, but this is where we're starting from. And we're hoping to start doing some more GNSS campaigns in other areas as well to supplement these measurements. So we can see that we have subsidence happening in southwestern Utah, central Utah near Pavant Valley and Levan, out on the western side of the Bonneville Salt Flats along the alluvial fan, where they have some pumping wells, and then in the northern portion of Salt Lake Valley near Bountiful and Woods Cross, and then near Clinton in Davis County. So I'm going to show a few examples of these subsiding areas, the first being down by Beryl Enterprise area. This is the largest spatial area that's subsiding in Utah. And in this area, there's been a groundwater level decline of 140 feet from 1948 to 2018, and there's little to no recovery of groundwater levels despite changes in precipitation over time. The plot that we can see in this slide, on the top we can see the cumulative displacement measured with InSAR, and then we can see a profile of the subsidence that's occurred over the past 10 years. So we can see up to a foot of displacement. I will also say I've now switched to imperial units because that's what the groundwater world uses. So apologies for that. But at least a foot we can think about conceptually here in the US. And then on the bottom, we see a time series point showing displacement from 2015 to 2025. The data that I'm showing here in blue and red are our locally processed measurements and the measurements that were automatically processed by the Opera displacement product I mentioned earlier to better understand if we can use that product moving forward without having to process everything ourselves. In this area, there's 114,000 acres that are subsiding at rates greater than 0.2 inches per year. And for comparison, this is about half the size of Davis County that is subsiding. The subsidence rates exceed 2.75 inches per year. And there's also an increase in the subsidence rate in the northwestern portion of this area. So again, we can see a profile cutting through that subsidence. The difference in those measurements are just due to the time frame that they're measuring. And then on the bottom, we can see that time series point, and we can see that inflection in the graph happening around 2021. And so this indicates that the extent of the subsidence signal is expanding and also accelerating in some areas. We estimate the total subsidence volume change over the past decade in this location, and we calculate about 95,000 acre feet of volume change due to subsidence, which corresponds to about 0.117 cubic kilometers. In addition to measuring the amount of volume change in these aquifer systems, we've also noticed, and this has been observed in other areas around the world, that faults that have been mapped can coincide with high gradients of displacement, indicating that these faults are acting as barriers to groundwater flow. Here's an example of cumulative displacement in Parowan Valley, where we can see those red areas, how they're bordered by the quaternary faults that have been mapped. And these areas also sometimes align with where earth fissures form. However, an interesting point here is that these are west dipping normal faults, and so subsidence is actually happening on that footwall. These maps we've been using as we go out and try to look for earth fissures in the field, and it can also, the subsidence signal can also be used to possibly help map blind faults that don't have an expression at the surface. Moving even closer to home, here we're going to talk briefly about some subsidence that's been happening near Woods Cross City. So in 2015, Woods Cross had noticed some damage to houses that was related to dewatering of shallow clays and possible decomposition of organic material. And so some homes were experiencing pretty significant damage. There was an InSAR study that was done back then in 2016 and did show subsidence over a larger area that was happening as well. And we updated these measurements to show that there is continued subsidence happening around Woods Cross and Bountiful of a lower rate than what we see down in southwestern Utah, but still almost up to a half a foot of displacement since 2016. In addition, just south of Woods Cross, there is the Big West oil refinery that started pumping from a well in 2020. And this is a pretty interesting example where you can see the aquifer response to that pumping directly. So the blue bars that are shown here are the monthly pumping rates that are available through the Utah division of water rights. And the deformation, we can see that subsidence starts. This is just really a small cone of depression around that well itself. We can see the start of subsidence with the onset of that pumping. We can see that pumping stops momentarily in 2022 and 2024. And during these time periods, we have a recovery of the pore fluid pressure and uplift in these locations. And then once that pumping starts again, we have that response of the pore fluid decrease. But then we do seem to have a leveling out of the subsidence at a certain point, depending on the amount of pumping that's occurring. So these types of observations in conjunction with groundwater levels are really useful to help understand aquifer properties. And we're hoping moving forward could also help constrain some type of sustainable withdrawal from wells if we want to avoid subsidence and permanent compaction. And I think one of the last examples that I want to provide is here in central Utah in Pavant Valley. Pavant Valley has one of the highest reported pumping rates in the state. So it's pumping more than 100,000 acre feet per year, and it's been pumping at that rate for at least 5 years, possibly longer. This is also the location, one of the locations in the state with the highest rates of displacement. And we can see more than 3 inches of displacement per year. And especially in the southern portion of Pavant Valley, we also see an increase in those displacement rates. So you can see there in 2022, in that bottom time series plot, we can see a very steep change in the displacement rates. Although I believe the pumping rate stayed similar, I know there was a drought in the 2020s in Utah. So we see these increases in or acceleration in the subsidence rates in multiple areas of the state, possibly related just to the natural recharge or lack of natural recharge to the system that season or in subsequent seasons. Another interesting observation from Pavant Valley is that we can see the dots in that top map are the 10-year groundwater level trends, and that they correspond quite well with the areas where we see that subsidence occurring. And this can also help us better understand the aquifer properties as well and help us constrain the amount of subsidence we might see for a given groundwater level decline. So to summarize the findings that we have in the state, here is a plot of Utah with the large red circles being the areas where we've measured subsidence and the total volume of subsidence that we've measured since the onset of Sentinel-1 acquisitions in 2015, 2016. The smaller dots are the monitoring wells and the 10-year groundwater level decline. So we see agreement, or we see that the subsiding areas correspond to where we have the groundwater level decline. But we do see there are regions where groundwater level is going down, but we don't yet see subsidence. And we mark these areas with the black dots. And here we do see some type of aquifer response to pumping and natural recharge. So there's a seasonal signal in these areas, but no long-term displacement of greater than about 0.3 inches per year. We identify these regions as susceptible to subsidence, and we'll continue monitoring them moving forward. Another way to visualize the previous plot in terms of cumulative subsidence volume, which can be related to aquifer storage loss in a confined aquifer, is this bar chart, which shows the total amount of cumulative subsidence from 2016 to 2025 divided into the different regions of Utah. So we can see that by far most of the subsidence is happening in southwestern Utah, with also a decent portion happening in the central portion of Utah as well. And really the majority of this subsidence volume change is happening in that Beryl Enterprise area, but we see increasing rates in other regions as well. So to answer our second science question, how much aquifer storage loss is occurring in Utah? We've found with this InSAR survey that 220,000 acres of land subsidence is happening in Utah at rates of greater than 0.3 inches per year. This is greater than 15% of the amount of irrigated land in Utah. The total volume changes from 2016 to 2017 to 2025 is greater than 130,000 acre feet, or about 0.16 cubic kilometers. And this corresponds to about 11 to 15% of yearly groundwater withdrawals across the entire state of Utah. Some perspectives and questions that we're still looking to answer using these data sets in combination with groundwater levels and pumping records is, can we constrain sustainable pumping rates in Utah? And can we constrain aquifer storage properties from those subsidence and groundwater levels? So again, here we have the conclusions from the two parts of this talk. That we can, at open vent volcanoes, we can have magma replenishment in a storage region without significant pressurization. And that in Utah, we have more than 130,000 acre feet of subsidence volume change since 2015. With the UGS, we're always looking for new ways to apply InSAR. We're hoping and validate these measurements. We're hoping to start conducting more GNSS campaigns throughout the state to better constrain the subsiding rates throughout these identified basins. We're also hoping to apply especially the InSAR data set to slow-moving landslides. Because of the capability of penetrating through vegetation, we're going to be able to have a better coverage statewide to be able to study these landslides. And then we have some other long-term goals related to measuring snow water equivalent with L-band InSAR, wetland mapping, and then disaster response in response to large earthquakes. And I think I will stop there and happy to answer any more questions. Yeah, so it would depend on the spatial extent of the signals. If it's very localized, it'd be more difficult just because of the resolution of the satellite, spatial resolution of the satellite. Also, if it's, in some cases, if you have too much displacement too fast that's occurring, that's also decorrelates the signal. So that can be an issue. One thing that we've found with some of my colleagues in hazards is that even if we can't pick up those like haphazard signals with the velocity rates, which assume constant rate of displacement over time, if you have some idea of where that's happening, you can do more targeted studies and look at like individual interferograms to be able to see if you can get some measurements through that. So it's more difficult to monitor on like a statewide side, but that with like the automated products that are being processed and the longer wavelengths, there could be some progress with that. Like the actual temporal component. So it's you're limited by when your acquisitions are. And so we don't have the temporal component. In this case, the magma at Ambrim, the magma migration happened over about a day and a half. And so in seismicity, we did see that migration, but because we just had one acquisition before that started and one acquisition after, we can only see the total displacement that happened. If you have an ideal situation where you have magma traveling tens of kilometers and you happen to have an acquisition in the middle of that, you can see the progression of the displacement field. And there are some pretty cool examples of that, I think, from like Iceland, or I've seen some at Piton de la Fournaise. So we don't have the, like for, the minute, hour, daily scale. Yeah, SAR's not quite there yet. Mm-hmm. Yeah, so there's going to be two components to the amount of volume lost. So there's both. So within with InSAR, we're assuming that the subsidence is mostly happening in a confined aquifer, and so you're having a pore fluid decrease, but then you can also have water level changes in the unconfined portion of the aquifer, and so it changes the saturation of that aquifer system. And so you would need additional observations or measurements in order to constrain that unconfined portion of the aquifer. In InSAR, we're seeing the displacement mostly in the fine grained sediments, like the aquitard portions. Yeah, thank you. Mm-hmm. I think because you have the unconfined portion of the aquifers that we're not taking into account, I think depending on your aquifer system, that might be a bit too simplistic. But that's a question probably for some of my colleagues in the groundwater program who could talk in much more detail about the different, they actually do the groundwater budgets throughout these different basins. So Greg just did one for Milford, and you could probably ask him more questions after. Yeah, so I realized that the units on the pumping rate aren't on that plot. I'm sorry, but this is an acre feet. So the monthly pumping rates reach above 100 acre feet in 2023. So in some of the areas in southwestern Utah, the pumping in the entire valley can reach up to 100,000 acre feet. But that's from mini wells. This is one single well we're getting the pumping measurements or withdrawals from.
Maybe
Yeah, it's possible. It depends on the magnitude, like how much deformation you're seeing. Also depends on whether or not you're expecting to see that. Yeah, like how far outside of the lake you're going to see it. If it was covered in water and then later it's not covered in water, that's not going to be coherent in InSAR observations. But if you see like a longer wavelength floating signal, it just depends on the amount of displacement. InSAR can't penetrate through water, so you're limited to the edges of the lake in that case. Um, elastic signals, we haven't looked directly at that. We've been looking mostly in the unconsolidated aquifers where we're seeing responses really to that seasonal pumping and the natural recharge in the winter. I know that in California, they've measured this with GNSS and also with InSAR. When they have the atmospheric rivers just dumping water, they'll see the loading of that water. So hypothetically, it could be measurable in Utah. We'd probably, we haven't looked at that yet, but it'd be interesting. Mm. Hmm. Um, so you go out in a boat and look at bathymetry. um, and there is a seafloor geodesy that is, I don't know too much about, but there are other techniques where you can look at deformation that's occurring on the seafloor. In this particular case, we didn't have any observations beneath the surface. There was talks of doing another bathymetric survey, but I don't think it's happened yet, and it's been quite a while, so I'm not sure when that's going to happen. But there have been some analyses of the pumice in terms of composition and some published papers regarding that from some of our colleagues. So they have been looking at like the petrology of those products compared to the ones that were erupted in the caldera. And there's some interesting findings regarding like the magma mixing within the chamber prior to the eruption and some timing of all that in those data sets.
Think, Cheryl, next week, our seminar will be something like